talking about primordial black holes and speculative eliminative. So yeah, sure we can start.
Yeah, great. Thank you so much to everyone for being here, and to Niels and Sana and then everyone else from the group for organizing this wonderful series. Yeah, I committed myself to talking about primordial black holes and the remnants, and I should say that this is okay. The origins of this are that like there's a like growing body of philosophical work on black holes generally, right? You know, we have papers on the phonology of particular lines of evidence, and on global structures, and on many definitions of black holes, and cosmic censorship, and link between black holes and space-time singularities. I'm just naming them in like totally random order. More historical papers on the origin of the notion of a black hole, and of course a bunch of papers on like Hawking radiation and black hole thermodynamics and all of this. But there's one kind of like area of research on black holes that's sort of like with little or not that much philosophical attention, and that's primordial black holes. And so 2 years ago, I think this was still like when things were like largely in COVID and online. Mike Schneider and we ran like a kind of like a brief reading group on primordial black holes, and that was actually grew up from the series of seminars that Niels organized. That's kind of like at the moment transformed into this meeting that I'm here. So it's a beautiful loop in a way. And so we met like a bunch of times and read a bunch of papers, and now I should say that, well, now I'll present some of it, but I should have said that, you know, there's a caveat, which is, first of all, that this version of the talk is very, very much work in progress. I don't know how much of this will end up in the final paper, because, oh my God, I'm being recorded, but I will say this anyway. Well, so this time I am the shitty co-author, and not like, I don't want to throw any shade of Mike, but like, I want to throw shade of myself. I'm the bad co-author, and I've been like super slow with my bit. And also this version of slide is not endorsed by Mike, simply because I just finished them in no time for Mike to have a look at it. So I would like to credit all the good parts of this talk, if there are any, to Mike, and all of the others to myself. But you know, like this is sort of joint work. The ambition is to have like a joint paper about this at some point. It grows from this thing, and I don't know. I hope you will like it, and I hope there will be. I think there are some interesting things about primordial black holes that one can look at from a kind of like philosophical angle, and hopefully it will be fun. But if not, well, maybe I'm just confused about things. That happens all the time. Okay. So, well, the plan for this talk is like really simple. Like it has basically two sections. The first is kind of like some like basic information about the physics of primordial black holes and the remnants, and how these are used as dark matter candidates. And then the second section will be kind of like me, providing sort of like a philosophical assessment of a program of search for the primordial black holes and the remnants, and kind of like all sorts of, I think, interesting philosophical things that can be said about it. And hopefully they're not too confused, because the bar, as I said, is low. There's little to no sort of like philosophy of science engagement, as far as I know. Probably I missed something, but you know, hopefully there are some interesting things that can be said about this.
So this terminology seems to suggest that the remnants are not themselves black holes anymore, but they are, right?
Okay, I would say, I would say that kind of like really depends on your take on what a remnant is. I would think that like that it's like a model. It really strongly depends on what you mean by a remnant. So if you mean by this that like we can kind of like jump to the remnant from the outside that we can never escape, I don't know. But like probably, I guess. Okay, so just so we're all on the same page, right? Like when we talk about black hole remnant, it's sort of like one of the ways of resolving the information loss paradox, where sort of like the black hole forms, starts to evaporate, and then at some point it kind of like stops and remains in this, you know, like maximally informationally dense state. And so is that still a black hole or not? I think it really depends on the model. So in this like black to white hole transition model, which I will discuss a little bit, and which some of the authors like Ravelli, Caravelli, and others try to present as a remnants type of solution, they're, well, in a way they're not black holes because the end state is a white hole. So it has an anti-trapped surface, so to speak, right? It doesn't have a trapped surface. We cannot come from the outside, and it like transitions into a non-singular space someone and so in a way in those models they do not have many of the features of black holes. There is the event horizon is gone, the singularity is gone. In some other models, I think one could sort of see them as black hole-like in the sense that like the evaporation process ends, and then we're left with this like very, very dense kind of thing that sort of like continues forever unchanged throughout the evolution of the universe. Yeah. But here I will be to some extent interested in the remnants of primordial black holes. I mean, not just me, like other people in the literature are interested in them. Okay. Yeah, so to continue being on the same page, I should say, what are the primordial black holes? I'm assuming that we have some kind of like a working intuition what a black hole is. Hopefully at this series I can just do that. And yeah, and then the very basic thing I have to say is that primordial black holes are supposed to form from fluctuations in the very early stages of the universe. So maybe towards the end of the inflation era, maybe early radiation-dominated era, circa 1 second after Big Bang or so, like kind of around that time. And both primordial black holes and to a smaller extent the remnants are kind of like, I think it's fair to say, regularly proposed in theoretical physics literature as dark matter candidates within the lambda CDM cosmological model. And I couldn't resist that quote in Juliusz's paper on dark matter realism for some philosophical context. So in the context of a kind of like thinnest common core concept of dark matter, Juliusz considers this characterization of, well, dark matter is whatever stuff kind of like accounts for dark matter effect, and rightly points out that stuff is a very vague thing because this common core concept covers almost anything, and dark matter may be a type of particle that acts as a phonons or collective excitations of a Bose-Einstein condensate. Maybe it could be a whole dark sector. Maybe it doesn't even need to consist of particles, but could be made up of primordial black holes, or maybe just an illusion or modified gravity or so, or whatever. And so here we're, yeah, so
yeah, the screen.
Oh, the screen just doesn't capture this. That's amazing. Okay, yeah. So here I'm kind of like in a way I think part of the sort of like also like, because I'm trying to sell this as I don't need to sell this, like I'm an academic, I don't sell anything, but you know, like I'm trying to kind of like justify the reason also for looking at primordial black holes as, you know, it's sort of like a way of making of kind of like having like a clear ontology in a way of it's a candidate for a clear ontology of the dark matter component of lambda CDM in a way, right? So that's also like pretty cool. That's in itself like worth philosophical attention, maybe. And it will actually get more complicated in a moment, because one of the things that physicists working on primordial black holes nowadays propose is that oh, maybe the dark matter sector consists of some primordial black holes and then some other kind of like, I don't know, WIMPs or axions or whatsoever. So it's a kind of like, it's in a way it's kind of like none of these options, but even more messy.
You mentioned the fluctuations could be at the start of inflation or the end. If they would be at the start, what would happen to the black hole? Would inflation not like either wash them out or make them huge black holes, or would nothing change? It's just space expanding, but the black hole.
Okay, so that I'm not covering this on the slides, but that kind of like depends on the formation channel. And the simplest formation channel is, we have some inhomogeneities, and some of them will be kind of like dense enough to just undergo like the normal gravitational collapse. And I guess that would happen at the start of inflation or at the end of it. But I think typically people consider this sort of situations to happen at the end of inflation.
Yeah, because it seems like the inflation would counteract the collapse. Or
yeah, because it tracks so rapidly.
Everything would become
Yeah.
larger than it. That's right. So
However, there are also these proposals that sometimes arise in the context of big bounce type scenarios, where we do have, some kind of like maybe like a very small black hole traveling from the previous universe to the current universe, and if they're already there, formed, at the onset of the inflation, and they would presumably kind of like just persist through the inflation because they're sort of like already formed, so to speak. And I think for many purposes, at least for the purpose of like coming up with a dark matter model, those would be kind of like equally good as the primordial black holes that kind of like properly formed through gravitational collapse or whatever other mechanism at the end of the inflation.
which would need a hell of a lot to have a reasonable density left, right? If they're coming before inflation, and you blow up the universe.
Oh yeah.
But,
Yeah.
okay.
Yeah. I should also say that I'm totally happy with questions during the talk, so please like hit me with anything. Okay. Yeah, so all right, so I said what are the primordial black holes? That's good. So now let's look at a very brief history. So I'll just kind of like sketch through like reasoning that happens in some of the classical papers. So I should maybe say this that I was ashamed to discover it so late, although it's in the papers. I just read them carelessly. But as a matter of fact, the first person who seems to propose the idea of primordial black holes is the Russian theoretical physicist Zeldovich in 1966. Then there are some papers in 1967 with Novikov. But when I started reading about primordial black holes, and also the reading group, we just started with Hawking 1971. And it's an interesting thing that Hawking doesn't cite Zeldovich's work on primordial black holes at all. I don't know if he was aware of it or not. I think it's a funny and maybe a bit delicate historical question, these kinds of descriptions. But I don't know how influential Zeldovich's idea sort of like was in those early stages. I think it's, I would be like super honest about all kinds of loops and loopholes in the talk. And so I think this is like the spread of this is an interesting historical question and so on.
Well, Hawking visited Zeldovich in the PhD.
Right. Yeah. But he does not cite Zeldovich in this 1971 paper.
Yeah. But I mean, he knew Zeldovich and he knew what he was working on. So.
Yeah. And it's not just this paper. Like if you look at this paper by Novikov, Stravinsky, Zeldovich, and I forgot who else. They give you like a bunch of Zeldovich's paper on papers on the topic from like late 60s. Yeah. And so, okay, so now let's look briefly at Hawking 1971. And I still haven't looked at Zeldovich in 66 myself, so I don't know what's the topical overlap. But like basically what happens in Hawking is, and this is okay. I'll first tell you what happens in the paper, and then I'll tell you like why it's fun. This can already see that here. So this is so we're in 1971, and Hawking, considers this. So this is around this time, like from an observational point of view, black holes are starting to become entrenched, right? It's like post-Lynden-Bell model of AGMs and quasars, and now Hawking considers this possibility that apart from those like big size black holes, there may also be a large number of what he calls collapsed objects. I think the terminology is still like a bit in flux at the time, of very much smaller, and by this he means than the galactic center, which he considered in the previous paragraph, a very much smaller mass, which were formed in the very early stages of the universe. He sort of like considers this as something that kind of like naturally follows from Charles Misner's chaotic cosmology model. And what happens in Misner's chaotic cosmology is that like Misner's tried to avoid postulating a very special initial condition to explain the existence of galaxies, but rather sort of say whatever the initial condition was, it was characterized by like certain physical assumption, and the assumption was that there were very large random fluctuations at all length scales, and most of those were later damped. And then Hawking does this in the paper, does the kind of like like an estimate of, well, but if we have this like early stage of the universe, and things are sort of like randomly chaotic or strongly chaotically distributed, then for some of those there would be like regions where the kind of like gravitational energy, I have no idea what he meant by this in 1971, dominate, and in particular the kind of like gravitational interactions in those regions would be stronger than the kind of like kinetic energy driving expansion. I think this is pre-inflationary. This is not an inflationary cosmology model, right? Like we don't need inflation to like get these kinds of situations going. I think, well, so for those regions, the gravitational energy would dominate, and they would just collapse in the standard gravitational collapse. And what then happens in Hawking, he estimates, how large could they be, and then goes on to analyze, possible observational effects. And that's where the paper becomes really kind of like fun to read from contemporary perspective, because this is a time where Joe Weber's attempts to detect gravitational waves with those like bar detectors were still considered to be like many people still, I think at the time in 1971, most people even considered this to be like a reliable signal, reliable detection, and so Hawking in the paper kind of like takes it for granted that Weber's detections of gravitational waves or observations of gravitational waves are genuine. And he then suggests that like a possible source of the signal that Weber observes would be something like a primordial black hole devouring like a neutron star. And kind of like the late stages of that would be what we see in Weber's observations. It's just a brief, it's just a historical trivia, because of course now no one thinks that Weber's observations were any good, so there was no signal to explain whatsoever. But in 1971, Hawking still thinks it. Okay, and so this is sort of like one way in the early 70s where primordial black holes sort of like show up, and then also fairly early, primordial black holes are linked to the effect that we now call the Hawking radiation. So, for instance, in Hawking 74, this is like a Nature paper. I think it's called Black Hole Explosions. And so in this paper, he kind of like outlines the calculation of what we now call the Hawking radiation, namely that black holes emit this like thermal radiation and hence have a finite lifespan. And of course, he's like immediately concerned with, well, but can we see this effect? Because that effect is inversely proportional to the mass of a black hole. And he says that for a black hole of solar mass, this and by this he means time to final evaporation is or time takes a black hole to fully evaporate is much longer than the age of the universe. There might, however, be much smaller black holes which perform the fluctuations in the early universe and continues to kind of like discuss some observable effects one could extract out of those. And so, and I think it's indeed fair to say that like life would be beautiful if we had primordial black holes of, you know, just the right kind of just the right amount of mass, because that would be like the best way of actually confirming the existence of astrophysical Hawking radiation. So they would need to be, you know, as you will see in the plots from basically taken from Bernard Carr that I will discuss later on, that like they would need to be, you know, like massive enough to not be kind of completely evaporated by now, but not too big, so that we could sort of like see the late stages where this thermal emission would become kind of like energetic enough. And so life would be great if we had them. Is life great? Well, I think we all know that. But in the context of dark matter, McGibbon in '87 also this idea that primordial black holes could sort of like serve as dark matter candidates, I think this is like fairly old. I think this goes like this is definitely happens in the 1970s. But McGibbon in '87 considers the idea that it's not the primordial black holes themselves, but their remnants of the late stages of their evaporation, that it is that provides us with the dark matter candidate. And so there will be throughout this talk, there will be sort of a symmetry between, you know, like looking at the primordial black holes as dark matter candidates and as the remnants of primordial black holes as dark matter candidates. And there will be, you know, they're both speculative, but the remnants are much more speculative than the primordial black holes, right? Simply because, well, so many other things could happen in the course of evaporation, so many solutions to the information loss problem. Remnants are just one of them, and so there are like layers of additional speculation sort of happening. Yeah, and so in this really it's like a fun but super short paper. So some of the details are not very clear to me, but like basically what happens there is that McGibbon begins with the phenomenon of black hole evaporation and says, well, there are essentially three possibilities for Planck-sized black holes, so those which are at the end of the evaporation. Maybe they turn into a stable object that kind of like continues to persist. So this is sort of what we talked about earlier in response to Nils's question. Maybe it's a naked singularity or some other like information devouring singularity, or maybe there's a kind of like final burst and like a non-singular transition to just kind of like normal kind of space-time. And then McGibbon kind of like outlines the ways in which the first of these, so the stable remnants, would behave like the cold dark matter. And you know, it's not just like those papers from 1970s or 1980s. Like primordial black holes and the remnants continue to show up in the literature. So I'll just give you like two examples. The first is this very recent paper by Delos and Silk, where they consider one of those like mixed primordial black holes and particle dark matter scenarios. So it's sort of like, well, it's not that the whole of dark matter consists of primordial black holes, but some proportion consists of primordial black holes, and some consists of some kind of like a particle scenario. And they claim that the calculations that they do show that it's possible that primordial black holes that contribute only like a 1% level fraction of dark matter can be accompanied by ultra-dense halos that nevertheless comprise an order of unity fraction of dark matter. And the halos consist of either this particle dark matter or much smaller primordial black holes, kind of like gravitationally bound in this. So I make no claims as to the plausibility of this model. What's I think enough for my purpose is that, that's like this is alive stuff, right? Like every now and then you will see someone positing some kind of like a primordial black hole model, and not just primordial black hole, because, and I will discuss this later on in a bit more detail. There are also people like Carlo Rovelli and Francesca Bidotta who suggest that, well, maybe it's not primordial black holes themselves, but kind of like loop quantum gravity derived remnants of primordial black holes that could account for dark matter. So this is kind of like a contemporary version of McGibbon in a way, in the spirit, so to speak. But those are by far not the only candidates. You could also look at this, the final sections of this great overview of primordial black holes by Bernard Card and Florian Kuno for a few other remnant candidates derived from all kinds of like ways in which string theorists and other physicists try to like solve the information loss paradox. Okay, well, so now we went through what are the primordial black holes. We went through a brief history of primordial black holes, and I think it's very fair to say, to ask, are there primordial black holes? And and I think this is where things become maybe less physically exciting, but philosophically more fascinating, because we are now at the stage where there was almost 60 years of research on primordial black holes, right? If you count from like Zeldovich 1966, it's yeah, we're getting there. And all of this research ended up only negative outcomes. And I will substantiate that with some plots in just a moment. Like I will show you a plot from the 1970s and a plot from a few years ago to sort of demonstrate what kind of progress on this research program there has been. But I think the fact that it's like almost like 60 years of negative results makes this a really fascinating target for philosophical analysis. Because, well, first of all, how to evaluate such a program? Like, should we continue searching for primordial black holes? Are these models plausible? Is there kind of like a pessimistic meta-induction kind of thing happening? Like what's going on? Why physicists still do that? Like, is 50 or whatever years not enough to drop this idea? Are ideas ever dropped? So how to evaluate this? And then in close connection, like what kind of roles do primordial black holes play in physical theorizing? Is there something good about these kinds of like things? And in particular, it gets kind of like more detailed now, is does the speculative status of primordial black holes, and in particular the remnants, does this like automatically diminish their attractiveness as dark matter candidates, or can something be said in the defense of this program? I think I actually won't answer this one in the talk. Well, not in a clear way. And I think it's also an interesting question, like what kind of empirical search is this? Like how to characterize what physicists are doing, what they produce in the plots, like the plots I'm gonna show you in a moment.
The first question you said, should we still continue to research this? I mean, that's the binary question. Why not? What should the question be? How many of us physicists should still?
Right. Yeah. Of course. That could be the question of like how promising this sort of a thing is. Yeah. Okay, so are there primordial black holes? So here's a plot from Bernard Karp's paper from 1975, and it's so basically like what we see here is, you know, like what in mid 1970s Bernard Karp considered to be the observational limits on the density of primordial black holes in various mass ranges. So it's sort of like, you know, like the shaded bits are those that are like were like basically I think ruled out, and the white regions are what is being allowed in the 1970s. In the units of critical density and the masses in grams, and I think there's I actually don't remember at the moment which of boxes is what. So go to the source directly. I'll be happy to send you the paper, but this is sort of like what is being allowed by the observation book like in the 1970s. And now here's a different diagram, also from a paper by Bernard Karp, who I should have said is like a relentless champion of the research on primordial black holes in the best possible way. And you know, on this plot, we see the allowed regions for primordial black holes, in the sense that like those kind of like colored bits are what is being ruled out by various types of arguments and observations. And so in particular, you will see that like there are these kinds of like four promising kind of like areas where kind of like some form of a primordial black hole could sort of still live, but all of those colored ones are ruled out by various observations. And so, you know, like that's what the progress on the question of primordial black holes looks like. And so in this diagram, those are all kinds of, like diagram summarize all kinds of constraints. So there are constraints from evaporation in red, the gravitational lensing in blue, gravitational waves, I think it's this like small gray thing up there. Various dynamical effects, accretion effects, CMB distortions, and a bunch of other observations. Like you can, like, I will not read this all. There's like a lot of things sort of that kind of when combined, if we trust that they were kind of like combined in the right way, give us these limits. And there's also I think the particularly fun limit is the incredulity limit, which corresponds to there being just one primordial black hole per relevant experiment. So if you look at galaxy, maybe there's just one in the whole galaxy, but then you look at the galaxy cluster, maybe there's again just one. Then you look at the universe, and maybe there's just one. And the upshot of this is that like for Karp, there are these like basically like four regions, like this little bump, and these two. And you could see immediately, because this axis up here, up top, is the is the mass spectrum. They're very far up from one another, right? This is kind of like close to, I don't know, like 10 to minus 15 grams, but this is 10 to 15. And so the kind of like allowed mass ranges are very, very far from each other.
How is these still possible? How would we not have noticed such masses? Because the density would be so low.
Here?
No, the region B. How could we have missed? Can we not have ruled out such?
Yeah, it's a good question. How could we how could we miss so massive ones? The question.
Yeah. Or I guess that is we see the dark matter, we just don't know if it's like or not.
Yeah, exactly. You see some kind of like a dark matter effect, right? In principle, it's this is what is not ruled out yet. So, yeah. Yeah. Okay, so now some comments on this diagram. That first of all, the diagram above has numerous assumptions, and in particular, there's what is in this literature called a monochromatic assumption that the mass function is monochromatic, namely that all of the primordial black holes have the same mass. And of course, now you could ask, well, okay, that's a assumption significant enough that the physicist uses this in the first line of a description of a diagram. So, but that would open a DM2M type problem. How much of the diagram remains valid outside of it if we drop this assumption, right? And that's a great question. I tried to answer this for myself, and I came up with finding conflicting answers in the literature. So I will just summarize them for you. So some authors claim that if we drop this assumption, we might get stronger constraints, because they say for fixed primordial black hole density, we conclude that an extended mass function is always more strongly constrained than a monochromatic one for some kinds of constraints. On the other hand, other authors say that the constraints on the fraction of dark matter are relaxed when we're considering an extended distribution. So I have no idea who to trust. I think it's just fair to say that it becomes quite messy when we drop this simplifying assumptions. And I think also a bigger question in the background, and we have already seen that in this Silk paper on where they considered supermassive halos that comprise with just the 1% of primordial black holes, but then a bunch of dark matter particles is, well, should primordial black holes and or the remnants actually that constitute all of dark matter or just a fraction of dark matter? How big of a fraction? And from diagram we see that there's only a small range where they could account for all of dark matter, right? Those bumps. But then one could play this game of, which I understand is what Silk and collaborators are doing, of oh, maybe I will have a little bit of primordial black holes and a little bit of axions and a little bit of something else, and kind of play with this kind of a model building. And I think it's also important to point out that the constraints cover a very wide range of mass, right? And they largely do not overlap. A lot of these there's some overlap around here, from 10 to the 7th solar masses, and kind of around here. But other than that, there's basically the overlap between these constraints is not very large. And so if you're particularly suspicious about one of the constraints, that's also something that might influence your assessment of the diagram and therefore the whole research program. All right. Oh gosh, I wanted to also talk about this. Okay, so I should stop around 4:30, right?
Well, it's 4:15, but we interrupted you so much that it's...
All right, I'll try to speed it up a little. Okay. So yes, as we have already seen, actually, super early, because already by Hawking himself in 1974, part of attractiveness of primordial black holes comes from the fact that they can reach late stages of evaporation or evaporate completely, or be kind of finishing their evaporation kind of around here and now. Maybe not here, but kind of around now. So in the current cosmological epoch. and therefore they can, in principle, provide some evidence for astrophysical Hawking radiation. And so in this way, like if like I guess almost everyone these days, we trust in the derivation of the Hawking radiation, or in some of the many derivations of the Hawking radiation, primordial black holes also have to involve some kind of a solution to the information loss problem, and not the kind of like what David Wallace calls the more serious information loss problem occurring halfway through evaporation, but the final evaporation problem. And I think what is, and again, I'm kind of like, like circling around what I think is the most philosophically fascinating about all of this, simply because like no one wrote a kind of like, primordial black holes for philosophers paper, so I have to do it for myself kind of thing. I think as a result, primordial black holes involve somewhat speculative physics with regard to their formation, because there's a lot of, like what exactly are the initial conditions we're considering? Is there a bounds? Should we trust in inflationary models? How exactly the collapse happens? This is already kind of like somewhat speculative physics, which I think is also fair to say involves some form of quantum gravity research. So primordial black holes involve that with regard to their formation, but they also involve an even more speculative physics with regard to their end. And so from this perspective, you could say, well, maybe it's actually pretty good that we don't see any of them, because like that would involve physics we don't know at the formation and physics we don't know at the end. On the other hand, that would make it really great if we saw them, right? Because we could try to constrain this kind of like more speculative physics that way. And I should also say that of course there are numerous solutions to the information loss problem out there. There are remnants, but there's just information is lost. Maybe there's like a non-sync, like a it all gets released in the final form. Maybe it transitions to a separate universe. Maybe we don't need to solve the problem because holography. All kinds of solutions, and I think this is what makes this primordial black hole remnant solution much more speculative with regard to what happens here and now. And I think there's a common impulse that this speculative status of remnants kind of like diminishes their attractiveness or relevance to cosmology. And I think with Mike, we wanted to kind of like take a sort of like a stand against that and say, well, no, actually, like this is sort of like an opposite situation. We could like these. It's exactly these sorts of situations that provide like a very rich and fertile grounds for physical theory and speculation in a good way. And so the fact that the remnants are just kind of like one of many speculative solutions to information loss doesn't mean that we should like, stop thinking about them in the context of primordial black holes. I think I sort of like over many years, I sort of like warmed up to this proposal. So I'll now talk about it very briefly. So recently, some of the loop quantum gravity people suggested that some form of a non-singular bounce of an evaporating black hole could provide something like a stable remnant solution that would also function as to some extent as a dark matter particle. So if that would be the case, that would be really great, right? Because we're kind of like solving the information loss problem, solving the space-time singularity problem, and if this is right, then that would also solve some, at least, of a dark matter problem, and that would be great, wouldn't it? Of course, we should be skeptical about these kinds of like wondrous coincidence arguments. I take no further stand on this, but it would be really cool, right? Yeah, one of the things that Ravelli and Vidal to say about these models is that, about the remnant solutions more generally, is that, well, in this case, we have like very weak or very bad observational constraints on whether remnants could constitute a possible contribution to dark matter, right? because we don't really know what kind of like a mechanism or what would be the physical nature of the remnants. Recall that all of the graphs that I showed you, like they represent, the percentage of dark matter that primordial black holes contribute to, but nothing there is said about the remnants, apart from this kind of like a line on this side of the screen, because that was the part where those were the primordial black holes that were kind of like very small, and so they are evaporated by now, so they cannot contribute to whatever dark matter effects we have now. Yeah. And so what happens then in work by Rovelli and others is that they have a kind of like a candidate for a clarification for what the remnant could be, and their model is, we have this black hole forming here and now and evaporating, and then at some point, which so fortunately happens to be around half of the page time, which sort of solves both of the problems of information loss. The kind of like quantum gravity repulsive effects start to dominate, and the whole system transitions from a black to white hole. And then, assuming that the stability of this model can be somewhat established, the model sort of provides something that at least is a stable remnant of a black hole. And then again, if these black holes were primordial and would be kind of like evaporated right now, then they would be also transitioning into those remnant type things right now. And then maybe all kinds of observational signatures could be drawn from this, or some effects could be explained, like dark matter effects. I take no sense about the plausibility of this model, because I don't think it's my job as a philosopher to provide any of this. But I think it's just interesting to see that like primordial black holes can be used in these kind of like fascinating and interesting ways. Okay. So this is we have kind of like talked a bit about where primordial black holes come from, how we don't see them, and how great it would be if we saw them. But now let's try to do some philosophy about all of this. So I think it's fair to ask the question, okay, like, so what? And I will have kind of like four sort of like areas or of kind of like thinking about primordial black holes, and those will be well, the role of empirical input in quantum gravity research, something on eliminative reasoning, something on value of negative results, and then I will probably not talk about stability because I'm already over time. Okay, so we have learned some things about primordial black holes. Now, so what? Like, why, as philosophers, should we care? And I think as philosophers, we should care first and foremost for this reason, that primordial black holes and the remnants seem to provide a point at which theorizing about quantum gravity can be constrained with observations. Right? There is some contact with observation. And even if at the moment all this theorizing is constrained only through negative results, we don't see primordial black holes, hence any model that says, you would see this sort of like, particular effect that kind of like falls in the region that under, again, like additional background assumption is ruled out through the diagram I cited from Carr and Kuhnel. Like all of those models are also ruled out. Again, assuming that those background assumptions are possible. So in this way, we cannot determine, about this or that approach to quantum gravity, but we can constrain and rule some of them out. And I think it's a rare occurrence in the field of research, which is like widely seen as philosophers as primarily dominated by non-empirical considerations. I agree with this. It's primarily dominated or largely dominated by non-empirical considerations, but not fully. And primordial black holes provides one of entry points which, observations can be filled in. And as I already said, some particular scenarios can be ruled out. So I think it's important for us philosophers to be aware of these points of contact, especially when the point of contact is like so funky. It involves both the physics about the early universe and about kind of like current cosmological epoch. Somehow it's so rare. Okay. Now, how to think about those like 50-something years of the research of primordial black holes? I tend to look at this, so the value of the diagrams that I've shown you. I tend to see the value of this through something like an eliminative reasoning. Like we're ruling alternative hypotheses until only our preferred one remains, and I guess here the null hypothesis is that there are no primordial black holes. In general, I think something like eliminative reasoning in the context of black hole physics is quite widely spread out. So sometimes we compare like a variety of models. We rule out like parameterized deviations from the curve metric through, or we try to do that with the HT observations. Or we have like whole parameterized formalisms for testing deviations from the field equations. And so I would like to see the primordial black hole research along a similar lens, but I'm actually struggling with this, and that makes me kind of unhappy. But well, I guess that's the life of a philosopher, because that makes me unhappy. Because in the case of primordial black holes, like these constraints on even on the diagram from Carl and Finnell, the constraints are very heterogeneous. It's a mix of very different observations, right? With gravitational waves, with dynamical effects, like all kinds of things kind of like piled together. There are these like implausibility lines in the argument, but they're also just like theoretical arguments, right? Like whole region of the diagram is ruled out by assuming that, those would be too small to evaporate. But that assumes in turn that Hawking radiation can be like used on the par with actual observations. And as a philosopher, I'm not so comfortable with this, simply because I have no positive empirical evidence for Hawking radiation. In other words, there could just as well be a situation where those black holes never formed, and therefore they would have never operated, and the ones that we have actually do not operate. No, I'm not saying it's a plausible option, but it's a possible option. And so I'm kind of uncomfortable with these kinds of eliminative reasoning, because it combines constraints which have very different nature, and that's even before getting into the details of this. Like, are the errors independent? Of these things. Are we even tracking the systematic deviations and the systematic errors and observational errors and so on? Did you want to? Okay. And I think looking at this looking at this through the lens of eliminative reasoning is already hard for primordial black holes, but I think it becomes particularly troublesome in the case of remnants, because, well, I think it's fair to say that even though like maybe Rovelli and Vidotto have some kind of like a toy model that can be computed from quantum gravity in certain kinds of situations, the remnant phenomenology is largely unknown. So how strongly can they be constrained at all? Like, does it even make sense to start pretty similar diagram for remnants? I don't think so. And the very last thing that I want to talk about today is this value of negative results. This is what kind of like drew me to like thinking about primordial black holes. It's so amazing that we have like negative results for 50 years and they still kind of like remain a live theoretical possibility. So what should we think about this for kind of like a research program? Of course, I should not, if I think of this as an eliminative reasoning, like I should not expect it to ever be decisive, right? But what's the value of a negative result in the sense of like, oh, there's nothing in here outcome? So my friends who sort of like philosophize about high energy particle physics consider this like desert. Sometimes it's called a desert scenario, which is the scenario where like like the standard model of particle physics is right, and then there's no new physics for 20 orders of magnitude until the Planck scale. And in that case, I think they consider it a disaster. Because there's no new physics, there's nothing to discover. We're just making, like, if we made experiments to confirm that, we would just be ensuring that there's nothing new there. And it's just hard to be excited about working such a project, and it's even harder to justify funding it, right? But that seems to be the sort of like a situation with primordial black holes. Like maybe they're there, you have a bunch of observations, and all they show is like a primordial black hole desert. There's nothing in here. So is this should I consider this to be like a similar sort of like unfortunate circumstance like the Hep desert? I think what's important about this is that, like, in astronomy, whenever we increase precision of observations, some interesting outcome is almost bound to happen in any case. Like kind of like, it's not like I'm testing the hypothesis, oh, there's this new kind of like beyond standard model physics here. And if it's not there, I get nothing out of it. In astronomy, we almost always get something interesting out of increasing the precision of observations, at least I think so far. And so in that sense, it's much easier to justify going up with the precision observations with the resolution done in something like a research project on large colliders. And I think, moreover, in the case of primordial black holes, I think a lot of what goes into the kind of like diagram that we discussed is a kind of like an opportunistic search. It's not like we're building a dedicated observatory to search for primordial black holes. We don't have like a dedicated primordial black hole telescope or whatever, right? It's rather, we have these observations that we do for other purposes, and they happen to also be useful for the purpose of constraining primordial black holes. And I think this kind of like partially accounts for the continuing presence of primordial black holes as dark matter candidates. It's not like, it's a live theoretical option, because like some new evidence will show up and can be further used to constrain the plausibility of this. And given this what I think is this feature of precision of astronomy, that precision will always give us something, like we can always further constrain this model better, and we don't have to be so much worried about the desert scenario. I think. I don't know if that makes a lot of sense, but I hope it does, and I will keep this bit and just leave you with some bibliography. Thanks.